ratio too. Okay, so we just said what creates carbon dioxide is living organisms that are not photosynthetic, like us, dogs, birds. How is it? Now we've talked about some of these. How is, since we know carbon dioxide is like the bad greenhouse gas right now, although there are others, how is it naturally removed from the atmosphere, from the environment? Remember? Okay, the biggest thing is plants. And the plants do photosynthesis, they bring in carbon dioxide and then they pump out oxygen gas. There are others. We mentioned some of this when we did mountain building. When you have erosion of certain types of rock, it actually pulls carbon dioxide out of the air. That's one of the ones that we talked about. Another way that it's naturally yanked out of the atmosphere, specifically, it's still in the environment, but out of the atmosphere is by the ocean. The ocean loves to gobble up carbon dioxide. And it's basically a giant sink for it. However, if the ocean gets warm enough, we just talked about this with the last unit, its ability to pull out carbon dioxide from the atmosphere is hindered. So that whole increasing the temperature of the planet, it's a positive feedback. They keep building into each other. I don't know what temperature is specifically the breaking point of the ocean. I didn't look that up. We may not actually have an exact temperature. And we know once we hit about 78, 79, that's when the hurricanes start going crazy. But we're going to talk about a couple of other feedback mechanisms today. I'm not going to go through every single one. These notes are already, this part is already enough. Like I said, most of the other ones in this chain, or at least the rest of this week, are quite a bit shorter. This one's got a lot of pictures on it though. Carbon is in anything that has or is going to be alive, at least on this planet. The only other possible element, because we're carbon-based on this planet, the only, and it's not on these notes, the only other possible element that would behave like carbon to be the backbone for molecules, macromolecules like proteins and fats and stuff, is silicon. But those organisms wouldn't look like us. We don't know of any yet. They wouldn't look like us. They would look more, most likely glass-like. But we haven't found anything that would be silicon-based. For our knowledge, everything that exists is a carbon-based life form. Most of the physical structure, granite, limestone, sandstone, the different types of rocks that we talked about a while ago, is going to have carbon in it in some way, shape, or form. Oops, we go back one. The carbon itself doesn't hold, like the actual atom does not hold the energy that's necessary for life. It's what's between it and the bonds of other elements, specifically bonds with hydrogen, bonds with oxygen, because this substance right here, you should have seen multiple times. Glucose, I mean, not all hydrocarbons have oxygen in them, but this is fuel, and this is when we break, and I could, oh heck, I haven't drawn this in forever. I don't remember how to do it. And then oxygen here, who's it here? Oh, it's been so long since I've done organic and biochem. I'm not even going to try to 3D draw it. It's been forever. I'll have to look it up. But that hexagon that I was starting to draw on the board, when you break those lines, that's what releases energy. And then we have all different kinds of cycles you should have learned about in biology, like the Krebs cycle, the fatty acid, the synthesis, gluconeogenesis. I don't know how much you guys go into with biology. It's like the only major core science I've not taught. I don't want to at all, ever. So the whole things cannot be created or destroyed. And the questions are, so we asked Marty Pants, where did everything come from? We talked about that at the very beginning of the year, Big Bang. But the bonds are broken and those atoms get rearranged into different substances in some type of chemical change. And for us, we do it with digestion. And the whole the whole saying, you are what you eat, is a very true statement. When you like cut yourself or get straight, when your body starts repairing that tissue, it's doing it from the things that you've ingested. And so if you eat horribly or put bad things into your body that you're not supposed to, your body's going to incorporate those things into its own cells.
So on the beach.
If that's what you primarily eat, you're not necessarily going to turn in pizza, but the different, depending on whatever you eat on your pizza, those things are being now processed by your body, and that's used then to create new cells. This is a picture of a landfill, if you haven't figured that out yet. We used to just, heck, some countries still just throw their crap in the ocean, but it used to be that we would just dig these giant pits and just throw everything in it and cover it up. The problem is that removes things from this cycle, from this recycling, this natural recycling cycle. Whereas if like an animal dies, like the deer that was smacked right in front of the school, the vultures took care of it in like 2 hours. It was weird. That thing, its tissues are now being incorporated by these vultures, and they go off and poop and whatnot, or eaten by other things. So that's natural recycling of tissue.
So we send it all to space.
Well, it's definitely removing it from the system. So, I mean, most people, they recycle in some way, shape, or form. Some people are very adamant about doing it. So people don't do it all. But keeping these atoms in the system is important, because if they're removed, we can't get them back. Carbon-12 is normal, everyday carbon, the one that's on the periodic table. It's got a total of 12 atomic mass units of its nucleus. 6 of them are protons and 6 of them are neutrons. That is the building block for life. Now, there are other carbons. There's 2 other carbons, actually. But the stuff that's in here, glucose, C6H12O6, is what plants make. When you do this, you've got carbon dioxide and water is going to make oxygen gas, glucose. I'm not trying to trigger you guys with chemistry up on the board, but I understand chemistry. So this is what plants do. So they bring in the carbon dioxide. Let's do this a little bit. Is there one more on here? Yeah. They take in carbon dioxide and they use water from the ground, and within the stromata, they look like stacked green pancakes inside the chloroplasts. They then breathe out oxygen gas, and they make their tissues. They make glucose, and which then other animals, herbivores, come along and eat, and then other things come along and eat them, and so on and so forth. The energy from the sun and the water from the earth, bringing in carbon dioxide that living organisms breathe out, starts that chain back over again. Carbon, let's see, we've got tissue. Okay, so we've got glucose, we have protein, we have pure carbon, and then we have normal things that we eat. I can't tell you the number that would go here, which is why there's a little n. Now, I'm not going to make you guys be able to spit out biochemical pathways, but you should know that C6H12O6 is glucose. That's what plants make. Carbon-14 is different. We talked about that forever ago. That's the stuff that breaks down just over every 5,000 years or so, that we can use to date things that were once alive up to a certain point. Okay, once you don't have enough carbon-14 because you've had enough half-lives, that's when you use things like uranium. But it is a different isotope of carbon. The other one that I did not mention on here was carbon-13, but you don't need to know anything about carbon-13. And that is a carbonate structure. Let's see, where's it at? Is it the bottom one? Okay, the bottom one. That is a picture of limestone. I don't know where I yanked that from. I know I've seen stuff like that in Yellowstone. But that is a calcium carbonate structure. It's the same stuff that is actually in the shells of like clams and stuff, like coral. It's not necessarily like rock, but it's the same structure. The carbon-12 is the backbone, is the literal thing that other elements attach to make larger things called macromolecules, big molecules, which is essentially us. So we got sugar in our blood, depending on if you're diabetic or if you're like me and you're hypoglycemic, that's going to control how much sugar is actually present in your blood. I don't know if you're diabetic or hypoglycemic or know people who are. Proteins, our actual genetic material has got carbon in it as well. Lots of other things in DNA, phosphorus, nitrogen, phosphates, amino acids, all that stuff you guys should learn in biology, and I'm sure it is not in your brain anymore. So limestone, calcium carbonate, which is this stuff, it is dissolved within the ocean itself. We talked about that before. The oceans hold on to a poop ton of heat and a poop ton. Oh, gosh, my eyes. Oh, I need the horse out the trees to die. Not really. I'm just trying to live their life. But it's also in the atmosphere, the stuff that we breathe out, that plants breathe in. One big giant cycle. The problem is, when we produce more carbon dioxide, they can be naturally removed by Earth's processes themselves. That's the problem. It's like I said, we love to make stuff, especially plastics. Now, tomorrow we're going to do the nitrogen cycle, which has a part to do with the carbon cycle. Plants are, without plants and without bacteria, everything is cyclical and is a part of everything else. And we're definitely going to be building off of the water unit in this unit. A lot of the stuff that we just talked about is going to be mentioned again. I'm actually glad they gave me that TEEPS thing to build this class, because it's let me know you really should do this first. Yeah, I've got some stuff that was out of order, but at least it gave me a template to try to follow. So the carbon cycle cycles between two major things. The solid form of carbon, whether it be as a rock, it be as a, well, technically diamond, rock family, so what you think of as a rock, and then as gas. So we've got your solid forms, your proteins, your sugars, rocks. The solid form of carbon, depending on what carbon has chemically bound with, is going to change its chemical makeup. The carbon is still carbon. It's just, I mean, even with pure carbon, diamonds don't look like graphite. They're the same dang thing. It's just a different lattice structure, so it looks different. It's still pure carbon. But the carbon atoms that are in us, and I mentioned this when we did space, originally they were generated within the heart of stars, just like ours. And you've got stars that get swallowed up by black holes. You get black holes that spit crap back out. You get some stars that explode in supernovas. So that means that eventually all of that carbon ended up here 4.6 billion years ago. And the carbon in this hand and the carbon in this hand can come from two completely, totally different stars. You are literally made of stardust. That is where the elements are created. And they just get rearranged. And this is, think of like Legos. You get those kits and then you build it once and then it goes into a bucket. I don't know if you guys play with Legos. I'm hoping you do. And then you don't build the same thing ever again.
We got a cell phone.
Oh, really? I wish my kid was more into Legos. There's nothing worse than stepping on a Lego.
I jump on it.
Like, that's like, you guys probably have never played jacks before. Don't know what jacks are?
Yes.
Yeah, that's probably the worst thing that you can step on in the middle of the night. They didn't always used to have those little round balls on the end of them.
And they're good traps.
They hurt. Let me see if I got a bullet on here. Yeah, there is. So the plant brings in the carbon dioxide from the atmosphere, turns it into glucose. Along comes things like us, whether you are a vegetarian or a normal omnivore or more carnivore. Some people have different things. But you're taking that in and then you're transferring it, you're changing it from sugars, from glucose, into proteins and into fats. And if you eat too much, okay, it's going to store it as fat. Also, if you try to starve yourself and think, well, I'm just not going to eat and get skinny, your body's self-defense mechanism is to immediately store it as fat because we get more calories back from burning fat than we do protein or glucose. You get 4 from glucose, you get 4 from protein, you get, not that you should be drinking alcohol, you get 7 from alcohol, and you get 9 from fats. So I understand how all this works because I'm a human biochemistry major, but there's better ways to try to lose weight if you're trying to do that. Drink a bunch of water. But don't like kill yourself by drinking gallons at a time because that can kill you. Yeah. There you hit a point where your kidneys can only process it, like they can only go so fast. So like you can only pee it out so fast. And if you bring in way more than what your body can handle, your cells will explode like water balloons. Yeah.
Oh, I know how I want to go out.
No, you don't. That was something that happened with hazing, specific war fraternities and sororities.
Is that
It wasn't.
hard?
I don't know. I'm not going to find out. I'm sure it doesn't feel good to die from water hypotoxis. It starts with an H. And like I said, it is important to watch what you eat. I'm not saying that you have to like be a perfect person. It's just, I don't know. If you have a bad diet and you start eating well, you give it about a week or two and you're going to notice a huge difference in what you feel like and your sleep. All right, now when we die, you're all going to die. Sorry, but it's going to happen. Now I know that like now we treat bodies and we use caskets and or sometimes it's burned, cremated. But if somebody just dies out in the woods, right, just dies, nobody finds them, eventually bacteria is going to start breaking them down. Now, aerobic bacteria use oxygen. Anaerobic bacteria don't. And when we do the nitrogen cycle, and I don't know how many of you have had fish tanks, but for those of you that have had to cycle and start a fish tank, you're going to understand a lot more of what I'm talking about tomorrow than people who haven't dealt with it. If you have aerobic bacteria that breaks down something dead, it's going to give off carbon dioxide gas. That's just what happens, which is going to go into the atmosphere. If it is anaerobic, okay, so there's no oxygen, you can't bind oxygen to the carbon. It binds hydrogen to the carbon and it makes methane gas. These are both greenhouse gases, both of them. And methane is about 20 times worse than carbon dioxide is. Like one molecule of methane is 20 times more potent global warming wise than carbon dioxide is. So we'll get more into that. Probably Monday is when I'm going to do all of the greenhouse gases together. It stinks. Methane, it's essentially a cow fart or a cow burp. If you've ever been around cattle, not their poop, their gas. Thank you. And so this is essentially what's happening. So on the right, it's showing you that the ocean is absorbing 338. Well, this is just a percentage of what's going on here. So we've got 338 for the carbon dioxide coming in, and we've got 332 that are actually going out. So we have a net pull into the ocean of what, 6? And then when we deal with trees breathe in a value of 450, and then we have exiting for whatever from other organisms of 439. So here we have, I think the difference of this is a total of 17. Then we have animals, it's a sad panda. So us, not panda bears in general, we're producing 29. And if you add and subtract all of these, we actually have a net release into the atmosphere. We have a gain of carbon dioxide into the atmosphere. It keeps going and going and going. It gets worse and worse and worse, and we've got major heating going on because of the greenhouse gas. Most of the carbon and carbon dioxide is going to be either sucked up by the oceans or it's going to be sucked up by photosynthetic plants. Our biggest chunk is in calcite. And it's just been a while since we've done rocks, a while ago. We have a bunch of limestone. See, now it's warm in here. We have a bunch of limestone in our bedrock. Told you, this room is like, in the ocean, when it brings in too much carbon dioxide, which is what's happening right now, we have a big issue with our coral beds right now. They're being what's called bleached. They turn white. When they turn white, they're dead. We're trying to fix them. The reason why this is happening, only the barrier reef off of Australia is in bad shape. When you have too much carbon dioxide, it's going to react with hydrogen and it's going to make carbonic acid. Okay, it's not like the worst of acids, but it's acidic enough that it changes the chemistry of the water enough that it kills certain organisms, specifically our coral. And the coral beds are the foundation for your oceanic fish. Not all fish have to have coral, but those are the hot spots of life. You've seen Finding Nemo. That's where you find the bulk of fish. We are trying to repair our beds. There's all different kinds of environmental fishes, but you can't fix a bed that's been killed. You have to start a new bed. You essentially plant new coral, and you hope that it sticks. And you hope that the oceans don't acidify even worse. And I mean, when we did the extinction events, the way that the volcanoes throw out all that carbon dioxide and the oceans became acidic, this is what it became acidic with, is that carbonic acid. So it's CO2 plus H2O makes H2CO3. It's one carbon dioxide reacts with one water molecule and makes carbonic acid. I'm not going to make you be able to do the reaction, balance it, or anything like that, but that's the chemistry that's actually behind it. There's going to be a lot more chemistry in this section than any of the others. I'm just not going to make you go super deep into it. All right, this cycle has been okay for a very long time. Obviously, major volcanic eruptions are going to disrupt this, but the Earth has fixed this. It's just taken time after time after time. And then along comes us. And for a long time, we didn't really make that big of a difference. We were growing our own crops. We were just burying the dead. We didn't have, what's it called, formaldehyde or whatever the heck they used to embalm people. We didn't do any of that. We were more in balance with nature. Well, now with the Industrial Revolution, we figured out, and we've used fossil fuels for forever, burning coal. And the original forges to make weapons were coal forges. But for us, you have a fuel source with a hydrocarbon. It could be different numbers here. It could be methane, CH4. But we have a fuel source, and it needs oxygen to burn, and it's going to make water and carbon dioxide gas. I hope you guys went through this in chemistry or with biology. Sometimes your fuel source does have oxygen attached to it, like sugar. Doesn't have to. But carbon dioxide gas and water are greenhouse gases. Water vapor, not water, not liquid water. So we've got methane, we've got carbon dioxide, we've got water vapor, and we've also got what's called nitrous oxide. These are your four major greenhouse gases, and I'll go more in depth with that Monday. I just don't know if I'm going to push pollution in with that or not, because I don't know. It depends on how long the notes are. When I start looking through all the different college things on these that I pull my stuff from. And the way greenhouse gas works is it allows the radiation from the sun to come in, but it keeps the heat from being able to escape. And it just builds and builds and builds and builds and builds. there's not much we can do except to try to control how much of this we emit as a species. When you do burn fossil fuels, the original carbon dioxide that was stored in the plant material, well, it's coal. It's the most common fossil fuel that we use in this country is coal. Not all fossil fuels are coal. But you have the carbon dioxide that was brought in by plants from 100 to 400 million years ago that had been stored within the rock in the case of coal, or within the gas in the case of methane, or within the liquid in the case of oil, of petroleum or crude. It's been stored for millions, hundreds of millions of years. And then along comes us, and we're like, burn it. And we release that carbon dioxide back into the atmosphere that was trapped. Now, if you do not know what anthropogenic means, it means human related. It means us. The bulk of the methane comes specifically from cows. And it's literally a cow fart and a cow burp. Now we have natural methane, like reserves, pockets of methane that can bubble out of the oceans. That happens when the oceans get too hot. Once again, from increased carbon dioxide from us burning stuff. GHG is short for greenhouse gas. I don't want to have to keep typing that out. I probably should have just done FF for fossil fuel too, but I didn't do it. I might go back and change that. I've got some kids in sixth that they type slow. But it's not just cows, it's other stuff too. There was actually a study and a push trying to figure out if they could take the stomachs from kangaroos and surgically replace them into cows, because kangaroos do not produce methane and they're ruminants. They're like, I don't think anything ever came of that. But yeah, I've heard so many weird, messed up grants, like trying to figure out why were they making the shrimp run on the treadmill. Can't remember why they were doing that. That one was dumb. They were studying something. There's so many weird wastes of, I don't know. I guess all in the name of science. All right, so fracking. Fracking, you guys should be familiar with. That's a way that you shock the ground, essentially, to try to get the fossil fuels to be released. So, and I'm not sure if they did it for natural gas and oil. I want to say fracking was specifically shale oil, at least around here, and it was causing minor earthquakes because, like, you pull it out, you got a void, and the earth adjusts, and miniature earthquake. That's why that happened. What was that, like 10 years ago? Ish, something like that. Landfill and sewage, yum, yum, yum. When these things decompose, when poop decomposes and rotten food and animals, whatever else is in the landfill, they're going to release, in the presence of aerobic bacteria, carbon dioxide, in the presence of anaerobic bacteria, methane gas. Is the oxygen present or not? That's what's important. Cutting down trees. There's less plants to breathe in that carbon dioxide. And it's a major issue, not necessarily here as much as it is in other countries. Yes, we still cut down large areas, but we replant a lot better. There's always pushes to try to replace the things that have been cut down. A lot of countries don't, though. Then you're going to have, when you cut down trees, you have a darker area in relationship to the plants. It's going to absorb more heat. So it's just, like I say, everything just sort of makes it worse. We are in what is called a positive feedback loop. That means one thing happens and it makes the other one do it more, which makes the first thing do it even more, and it just keeps building and building and building. It's like a 4 or 5 step process. So heating will cause ice to melt. If ice reflects back to space, protects us. When ice melts and you have land that is now exposed, which is darker, or water, which is exposed, it's going to pull more heat in. Okay, so it absorbs more radiation, more light. Doesn't necessarily mean visible, like light, the sun, more radiation from the sun. When you have permafrost melt, which we don't have here, but like up in Siberia, it's going to release trapped carbon dioxide. It's going to release trapped methane. Warming oceans, methane will bubble out. And so this is all triggered for warming. When you have warmer oceans at the equator, we just did this. You have more evaporation, more water vapor in the air. Water vapor is a greenhouse gas. It's the most plentiful one. And then this caused all different kinds of issues that we talked about the other day. It makes the oceans more salty at the equator. It could possibly mess up that global conveyor belt. Warmer temperatures will dry out plants. You will have natural die-off. You will have natural fires. Now, forest fires aren't necessarily a bad thing. Like, they rejuvenate areas. I remember when Yellowstone burned in 88, was it 88? Like, over half of the park just went up like a tinderbox. But it rejuvenated the plants. There are some plants that do not have their offspring grow, their seeds do not germinate unless they've been through a fire. And I can't remember the name of that flower. I know it's red. Not trying to go too fast. Let's see, we should be close already. Do that. We're almost done. We got a couple more. Another picture. Clouds. There are different types of clouds. This is something else that we did a long time ago. And I said, this 6 weeks sort of brings everything together. There are different types of clouds. Stratus and nimbus and cumulonimbus. The cumulus clouds, the big puffy white ones that look like cotton balls, that's a negative feedback. That means they reflect, because they're white, radiation back into space. They protect us. Cirrus clouds, on the other hand, the thin wispy ones that are way up, they're water vapor, which is a greenhouse gas. So cumulus clouds help protect us, but cirrus clouds negate that effect because they trap, they keep, because they're vapor, they don't let that heat go back into space. It depends. Depends on, is it the big puffy one or is it the thin wispy one? Which I don't know what we have out there. Yeah, let's look at it. Ooh, I'm looking gray. Well, I don't think we're supposed to get more rain. I got hail last night. This wasn't big. Little downsized hail. It's a baseball size hail, like my sister got. All right, almost done. I don't know why there's a number 1 there. I need to go back and take that off. No idea why that's there. Okay, so what can we do as a species? Consume fewer fossil fuels. Now that's easier said than done. We have like those hybrid electric cars. There's a big push for that. I don't know if I'd ever do an electric car. There are some that actually they have solar panels on them, which is weird. Okay, they're not very common, okay, but there was a push for those at one point in time. I don't think that went very far. Just use less electricity in general. Okay, so like I know my parents always used to yell at me, telling me to turn the lights off because, you know, and like keep the door shut because you don't want to air condition outside. We now have a big push for solar. Like I'm having solar panels getting put on my roof. We have those big wind turbines. There's a big push for that. Water dams, like the Hoover Dam, hydroelectric power. There's a couple other things I could have put on here, but I'm gonna come back and do this when we do renewable resources on Friday. Recycling. You guys probably have never used a compost heap before. Composting. People used to do composting. Like when you get and finish all your food, you threw it in the bin and you'd stir it up every now and then you would use that as fertilizer for your plants. A lot of people don't do that anymore. Replanting trees that have been cut down. We're going to still have to cut down trees for lumber. For paper. And if you don't replenish them, you're going to run out of this resource. Like I said, our country is pretty gosh darn good with environmental, like trying to fix things that were damaged. Now, I don't know if we can ever completely prevent global warming. It's a natural cycle of this planet. Okay, if a gigantic volcano decides to go kaboom, there's not much we can do about it. In fact, there was one in Iceland. I don't know if it's still erupting, but it very recently decided to go boom. Not like blow the island up kind of boom, but it popped its top. So prevent might not be the right word here. Reduce global warming might be the better word here, because I don't think there's ever a way that we're going to be able to stop it. Because if we cross that tipping point, I don't think we'll hit a thermal maximum, at least not in our lifetime, I don't. But if we cross that tipping point, we're in trouble. All right, the last thing I have is this image, and you guys should have this in your canvas. So, and it's just showing you like this is, so we got this positive temperature goes up, you have got melting of the ice, you have less reflective ice, and you've got, in this case, they're talking about water, more absorption with water, more warming, more melting, more absorption. So this is what it means by the carbon, or this cycle, this carbon cycle. With this one showing, they were having issues with the Amazon. Now, I don't know how long ago this one, I pulled this one, because I'm not seeing a date on it. But when you have temperatures going up, you have the moisture that's actually taken out of the plants themselves. They dry, they will die, they will burn. They're going to release carbon dioxide that was trapped in their tissues, which is going to, you're going to have less oxygen and less pull in of carbon dioxide and less push out of oxygen gas. You're going to have less rain, and it just keeps going over and over and over again. So I could have gone a little bit more in depth with some of the other feedback mechanisms for the carbon cycle, but I think, yeah, there's no way I would have enough time to do it. So I'm going to pull this back. Let me stop my thing. And like I said, we'll do the nitrogen cycle. Nitrogen cycle is nowhere near us. And like I said, I don't know if any